Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. My name's Sam, and I'm here to help you create a math journey that you're proud of and that you enjoy, something you can come back to regularly. Math has a layer of negativity all around this world, and I'm here to help you pull off those layers of negativity and start building up these beautiful layers of enjoyment and delight. Thank you for tuning in, and I'll see you on the math practice. To practice math today, we need to focus on some vocab words that will help us look at this experience with a math perspective. First, linear relationships are when two quantities are related linearly. You can describe them like increasing, decreasing, stays the same, undefined. Next, proportional relationships are a linear relationship that starts at the origin at 0, 0. If a relationship has an increasing slope or rate of change, it's like it's climbing, so the line is increasing upward. An increasing slope that's shallower than a slope of 1 is less steep. It'd be easier to climb than the previous. A decreasing slope of an absolute value greater than 1, that is like a slide going downward. An undefined slope would be like a free fall if you would just be dropping from the sky. Take a look at your PDF enhancement. If you don't have it yet, click the link in the description below to see what the directions are for this activity. Today we're looking at changing quantities at home. Choose two changing quantities in your house. For example, the depth of water filling in a sink over time, or the number of objects on a table. Can you determine which parts of the situation are constant and which parts are changing? Which can be assigned a variable? Create an input-output table for your independent and dependent quantities. Can you create an equation that works in several different scenarios of the same situation? Then test the accuracy of your equation. Here we are at the whiteboard trying to consider, does my sink fill up at a constant rate of speed? Does the water height change at a constant rate of speed? I can use speed as my terminology here instead of rate of change because I'm measuring over time, and speed is measured over time. So I'm measuring inches over time. And what you see I've done here is the red line represents the data I took from my sink filling up when there were a bunch of dishes in there. And you see that the height of the water increases faster when there's a bunch of dishes in the sink versus the blue line, which shows the trial when I had very little dishes in the sink. So when there's few dishes in the sink, it makes sense that the water fills at a slower rate than when the dishes are in the sink, the water fills at a faster rate. So with linear relationships, we can say that these two look pretty linear. Now my line is wobbly, which yours might be too, because I'm connecting data points. And when you have data points from observations, you often want to do a scatter plot. So stay tuned. I'm going to use a graphing utility, graphing software, to show you what that would look like more precisely, and then we can look at a line of best fit. But for this, just to get an idea, I would say that my sink fills at a constant rate of speed, constant rate of change. And with data, you can take the last point and interpolate. So which means from 0, 0 to the maximum height of my sink. When I had dishes in it, it took about 6 minutes. And when I did not have dishes in it, it took about 6 minutes and 45 seconds, or 6 minutes and 3/4 of a minute. To determine the approximate slope of this line, I can say that the average speed is just dividing that maximum height by the time it took to reach it. So for when I had dishes in my sink, it looks like 7/6 as a decimal is 1.17. So this is telling me that the height of the water in my kitchen sink, Y, equals about 1.17 times the number of minutes. So this is saying that each minute the water level rises about 1.2 inches, let's say. Now, when I don't have dishes in my sink, or I have few dishes in my sink, it's increasing the height at a slower speed. So 7 divided by 6 3/4 is about 1.04. We could even be more numerically lazy, as Neil deGrasse Tyson says, and we could say that about every minute the water level rises about an inch. So This is our observation. Let's take a look at a graphing software to see what they think the line of best fit is. I'm interested to see if I say they, but if the software determines that the lines start at the origin, and if they do start at the origin or close to it, we could say that this is a proportional relationship. From our sketches here, I would say these are proportional because I know that at 0 minutes there is no water in my sink. So I connected them to the origin, but this might not be the best fit line, and these aren't even straight. So these are just sketches to help us think, but let's go take a look at the graphing utility. The line of best fit is the line that cuts through all the data points in a way where it minimizes the distance of all the points to the line. So my line of best fit was pretty close to the one that the calculator created, except it has a shallower slope than mine. My slope was greater than 1. This slope is less than 1. And it shifted it up. It doesn't say that it starts at 0, 0. It says it starts at y-intercept of 1/2. Meaning that at 0 minutes, the sink had already filled 1/2 an inch. What does that look like on the graphing device? So we can go to y equals, and then type in 1x plus 0.5, and then graph it. And you can see that that line fits the data pretty well. Signing off. Until next time.